since last meeting.
You did this ahead of time?
So you're well? Okay. So, one of my favorite set of demonstrations today. So, in particular this, which doesn't look super exciting, but it's the most fun thing ever. Okay. What are we going to talk about? Induction. Faraday Lenz's law to begin with. You already know this. There's Faraday Lenz's law. I'm going to give you an exercise right off the bat because I didn't have time to do it on Thursday. And so we're going to talk about that, how we do the exercise. Then I'm going to talk a little bit about how we can express Faraday Lenz law in a slightly different form. It has to do with replacing the induced EMF by a loop integral of the electric field. And it's introducing for us the idea of, again, this induced EMF, but also now an induced electric field, which is a little bit of a new thing, and it's a little bit subtle, so we'll explore that a little bit. This is a chapter in our textbook that I strongly encourage you to read, okay? It's very interesting material, and again, it's a little bit subtle at times, so I'm encouraging you to read this chapter more closely than you might typically do. Then we're going to talk about what's called motional EMF, which had to do with an EMF and possibly a current induced by moving a piece of conductor through a magnetic field. The associated phenomenon of so-called eddy currents, which I'll describe, and then we'll talk about energy and power considerations in those eddy currents. And again, a couple of really fun demonstrations associated with that. All being well, I'm going to give you another specific example, this time to do with time varying magnetic fields and the induced electric field. And then we'll wrap up, all being well, talking about generators and how we might use Faraday Lenz law to produce currents, essentially, so power. All right, so let me have you guys get started right off the bat. I wanted to work on this problem, which I didn't have time to do on Thursday, so it's still up there, fortunately. So here's the example. So I even wrote a wrong little prop, which I made on the way down. So what you're supposed to imagine is a ring of conductor, and that ring of conductor has been folded along one of its diameters. So it looks like this, okay? Let's hear it. Okay, so it's been folded to look like this from your perspective. It has a magnetic field, which is in red on the sketch behind me, which is passing through the center of this now folded loop in an angle like this, okay? So it's at 45 degrees to both halves of that loop. And it is not constant, it changes in time, okay? So what I want you to do, working with a neighbor, is take these parameters. We know the radius of these semicircles, 3.7 centimeters, they're perpendicular to each other, they look like this. We've got a uniform magnetic field in this orientation, which starts off at an initial value of 76 millitesla, that's the -3 Tesla, and it's reduced to 0 during a time interval of 4.5 milliseconds. Okay? So I want you to tell me what is the magnitude of the induced EMF and what direction is it induced in. Okay, off you go. So you guys are working.
Okay. Wow.
I'm going to give you maybe 5 minutes.
Still to break down the problem. It would take 7 minutes.
Yeah, very slow.
So for those of you just arriving,
My
we're going to do some work already, which is working with a neighbor on the problem in the middle
I think you're
chalkboard.
right about, yeah, the university is not in the city.
Hot take.
I'm going to talk about like how, Columbia University was in Harlem, but then they named it Morning Star, so they kind of
Oh, if anyone has not yet turned on the camera, please.
I did it. I already did it.
You did, thank you.
request that work study.
That should be paid.
All right, so get those neurons firing.
I know that. I feel like the method is like you're at a 45 degree everywhere. So I think it's just like the equation like sine. What
I'm still writing down the damn problem.
Yeah.
That's what I'm saying. It takes forever to write down this problem. And then he...
I really wish it I'll print out like okay. Well.
And then the magnetic flux is the integral of the field dot.
Many of you are just arriving, we're working on this middle problem.
I'm pretty sure it's lenses a lot.
Yeah, so you would do
Reparative.
you would do the magnetic field times area times sine 45 divided by
Oh, to get the part that's perpendicular of the B field. Wouldn't you just add the opposites of the two like semicircles? Like
yeah, but they're gonna be this like they're each gonna be 1/2 like the area of this sine 45.
Well, we know what the change in magnetic flux is. Because we know that we can calculate.
because yeah, sine of
Change in
45 is the same as sine.
Yeah, you're just gonna calculate the first one, then it goes to zero.
What about, are they just the same?
Or like, no, I think magnetic flux it would be area of a circle times magnetic field times sine 45.
Because it'll be the same.
Yeah. So, or I mean, one of them would technically be cosine, but like,
But the
so it
result
doesn't matter. Yeah.
Okay, so what are you doing?
Divided by
And then-
4.5 times that.
And then the B field changes over time. And then since the B field changes, there's a change in flux.
magnetic flux
And then
is
there's
just-
a change in flux.
Okay, 2 minutes left.
Is there a negative in there?
Well, it doesn't matter. That's just
We're doing
direction.
that.
Yeah. But I think as far as direction, your field is going this way, and it turns like.
Yeah, exactly.
I think it would go like around like this. If that, like, if you're looking at it, like, I don't even.
Unit seconds.
I would go counterclockwise. Do seconds. It's 4.5 volts. Oh no. It's a 4.5.
Oh, the negative will go anyways because it's end to beginning, so it's negative.
Well, I mean, the negative's only there for
I know, but I'm saying it's going away, okay?
your battery is low.
Micro coulombs, is that what we're doing? Or micro Teslas?
To be honest, I always use normal Teslas or I just convert it. Oh, micro. Oh, yeah. How much is micro? I should know this.
Area? Are you area?
Okay, 30 seconds.
One of the dumbest things. Freaking midterm. I did that wrong. So I lost a point for that. I was off by like a magnitude of like 4 inches. Like, I was off by 10. And I was like, yeah, that's dumb. Real dumb.
On the linear algebra midterm, I transposed the wrong way. I felt the original dumb, but
Be like that.
Okay, all right, so as the conversation dies down, we're asked to find the magnitude and direction of the induced EMF in this loop. And again, just so you know the geometry, it's a circular loop that's been folded across a diameter to give two pieces at 90 degrees to each other. The magnetic field passes through the center at 45 degrees here, and is changing in time, changing uniformly in time. Okay, so induced EMF, you know I'm going to use Faraday lenses ball. So there it is twice on the chalkboard. I need to figure out the magnetic flux, and then I need to figure out how it's changing in time. So first off, how am I going to figure out the magnetic flux passing through that loop? Jessica.
It's BA sin theta or BA sin theta for the flux.
Sorry, say it again. Go ahead.
Sorry?
Go ahead, say it again.
Negative dBA sin theta.
Don't do this yet, I just want the flux.
Of BA sin theta.
Okay, BA sine theta. Okay, so that's our, let's say, roughly general expression for the flux. So I need to know the magnitude of the field, the relevant area, and the angle between them. Okay, so let's elaborate on that a little bit, because it's obviously not a totally straightforward geometry. So the magnetic flux is, the magnetic field is whatever it is, okay? That's the thing that's going to time vary. What's the area, and then what's the sine theta for this thing? Okay? Go ahead, Jessica. I don't want to stop you mid-flow.
So what you do, I'm very confused about what the angle should be, because
Okay.
I feel like it should just be pi r squared for the total area, but each one's in a slightly different angle.
Okay, well, certainly they're in different angles for sure, so they're at 90 degrees to each other. The field is at 45 degrees like so. No, it looks like you wanted to say something.
Well, like, so the way you do this, do you like calculate the flux separately for each like half of the circle?
You probably should, though noting the symmetry you might find a shortcut. But yeah, you really ought to, I would suggest. So probably what you would want to do is just making sure that you did this in case the angle wasn't 45 degrees. Is you would want to take half the area, which is of course a half pi r squared, if this thing has a radius r. Take that as being a half pi r squared, and then the sine theta between the angle vector of that area and the magnetic field is what?
40. Well, okay. So like, where is the where are all the arrows pointing? Like, where is theta measured between? So it's between the
Yeah,
like.
I know this is really hard to draw in a way that isn't confusing, but okay. So there's my ring, and then the field is penetrating through the center, but it's at 45 degrees to both of those surfaces.
So is the surface oriented like? Is the area vector pointing like downward?
Mhm.
Okay. So then the angle between them would be 45 degrees, right?
Okay, so that would work for the upper shaded semicircle.
Yeah.
And then if we wanted to add for the vertical semicircle that is not shaded at present, what would I do there? Yeah. I'm terribly embarrassed. After all these weeks, I still forget your name. What's your name?
Delphine.
Delphine, thank you.
I think technically it'd be cosine 45 degrees, but you could like just smush it in with the
I
sine.
can smush it in, right, because of the symmetry of this thing. So in both cases, the angle is 45 degrees. So quickly, it would be E times, and then I'm smushing it in here, times 2 times, so I've got pi r squared over 2, because that's 1/2, but I've got 2 of these. And then let's say I have sine 45 degrees, something like that, okay? So I'm combining these two, and of course, because of the symmetry, that's exactly what we get, okay? So 2's cancel, I get this. All right, so now I've got an expression for the flux passing through this loop, depending only now on what the magnetic field is. But now I have to worry what the time rate of change of this is. So this should be then, let's see, pi r squared b over root 2, coming from the sine 45 degrees. So now I have to worry about the time rate of change of this thing. So it's minus d by dt, pi r squared b over root 2. Okay? And so the only thing that is explicitly changing with time, of course, is the magnetic field. So let me just continue on down here. So what is dB by dt in this case? So now we've got some particular parameters here, and I didn't explicitly say this, but it was a uniform reduction in the magnetic field. So what is dB by dt? Yeah.
Well, you know the magnetic field will go to 0, so you know the final one's going to be 0, so you can
Yeah.
just use the one flux you calculated,
Yeah.
and then divide by the time, in this case 4.5 milliseconds.
Good, okay. So 0 minus 76 millitesla, final minus initial, and then calculate it, but then if I multiply it by this stuff, it turns out to be about 5.1 times 10 to the negative 2 volts, okay? So with dV by dt, I've got a uniform reduction going from 76 millitesla to 0 over a 4.5 millisecond time interval. Calculate that and plug it into here, where I still need to fold in my IR squared over 2, with R being 3.7 centimeters, and I get this as the magnitude of the induced EMF, okay? So what's complicated here is simply the geometry, I think. And then we fold in our uniform reduction of BC. No.
Can a flux ever be negative?
Yeah, I mean, if you think about it, it purely depends on what direction you're defining your area vector, right?
Okay.
So, a little bit side comment, but not unrelated. Remember when we did, for example, a flux calculation with Gauss's law, and we got an enclosing surface around something. So our area vector is defined always to point outwards in that case. Now with magnetic fields, magnetic monopoles don't apparently exist in nature, so it's a little bit different situation. But you can imagine defining your area vector one way or the other, and then depending on how that relates to your magnetic field, you can either have a positive or negative flux. Okay?
Okay, so like because the area vectors, we say that they're both pointing inside, that they happen to both give positive sign like measurements. Like, would it ever like matter? Like, would you ever like, I don't know, have like a negative angle for sign, or like, I don't know.
So think about what the implications are. Maybe I would choose the other direction, and then everything would come in with a minus sign, right? But what I'm really going to care about here, notice that I put in part A, what is the magnitude? So I only care about the size of this thing. And then crucially, part B here, I'm asking what is the direction? Now in that sense, the sense in which you drew your area vectors would be important. But what I want you to do in part B is rather than worry about which direction you define your area vector, simply think of Lenz's law, which is this oppositional nature of the induction phenomenon, and to say that the EMF will be induced in such a way to try and oppose whatever it is that is changing. So this is the subtle thing that I want you guys to tell me the answer to for part B now. So now you know that it's inducing an EMF of about 50 millivolts. The question is, what direction is it if I think about the orientation of this loop? Okay? So you tell me, what direction is the EMF induced in this thing? Right at the back.
We try to like induce currents in a way that gives superposition for both sides and would produce a magnetic field that's opposite.
Yeah, good. Right? So again, this oppositional behavior, whatever this is, it wants to induce an EMF and therefore a current in such a way that it's producing a magnetic field that's opposing whatever's changing. Now, the magnetic field is decreasing in this orientation. So the induced EMF wants to be in current in such a way that it's going to try and induce a magnetic field in this direction because it wants to oppose the decrease. Okay? Now here the geometry is really tricky, but by my reckoning, if I want to induce a magnetic field that's pointing in that direction, I better have my EMF and therefore current circulating around like so. Yes?
I think I'm just a little confused. So if the magnetic field is decreasing, shouldn't it increase it in this direction?
Oh, thank you.
Oh,
Yes.
no.
Sorry. Yes. Absolutely. So you want to increase it. I'm sorry. It's decreasing. I was thinking it's increasing. Of course, it's decreasing. Thank you. So indeed, I want to amplify it because it's decreasing. Thank you. So in that sense, like this. Okay. So you can see how easy it is to get confused. All right. So scratch those comments from 30 seconds ago and listen to Delphine and Noah, who correctly want to have it go in this direction. All right, good, yeah.
For this example, the value of sine 45 and cos 45 is the same, but why would you use sine?
Yeah, I guess if I was doing the correct definition with the scalar product, right, I would probably more correctly put in a cosine from, where is it, 5. You're right, in that sense, I would be more consistent in the Okay, so hopefully I don't screw it up a third time. So indeed, the field is decreasing in this direction, okay? So whatever I'm inducing wants to oppose that, which is to say it wants to increase it again, not go in the other direction. So if it wants to add to the magnetic field in that direction, my right-hand rule would suggest that as I look at this from that orientation, I should have current flowing around what looks like, I think from your perspective, clockwise, right? And then it's going to produce a magnetic field that is in that direction.
That's the direction of the EMF.
Yeah. Right? You're good? Well, not sure. So again, so I want to increase the field in that 45-degree direction, so through there. In order to do so, if I have current flowing around in this direction, I presumably have a magnetic field like so, right? Yeah? Yeah, of course it's essential that you look at this from, the direction that you're consistent. Turned it to the left. Like that? Like that? Okay, let's talk offline. So you can see how easy it's getting to get confused. Okay. Now usually you're not going to have a geometry that has a 90-degree bends in it like this, so it's a little bit easier. And for the other examples this morning, hopefully it will be more straightforward. Okay, so let's move on. Let me get rid of this. So now I want to talk about Faraday's law in terms of electric field. So consider the following. We've got a, let's say, circular loop of conducting wire. And it's embedded in the magnetic field pointing into the plane of the board. Now let's see if I get this right this time. Let's say if the magnetic field is increasing, in this case, what direction do you expect an EMF and in this case an induced current? Okay? So you tell me the magnetic field is increasing. Those X's mean the field is going into the plane of the board. Yeah.
They sound like a counterclockwise current, so that like the right hand rule it produces.
Okay, good. This time I think I'm in agreement correctly with you. So yeah, if the field is increasing in that direction, I want to induce an EMF and a current which opposes it. So I want to add a magnetic field component that's coming towards me. Okay? So indeed, I'm going to expect an EMF, and again, the conducting loop here, the current that is counterclockwise. We good this time? Okay? All right, yeah. So, this is indeed true. And so if we have a current here, an EMF, there must be an electric field that's driving this current, EMF essentially. And it turns out that this electric field, which is now an induced electric field, we'll talk about the meaning of that in just a moment, is there even if the conductor is not. Okay, let's say that again. So this induced electric field produced by a changing magnetic field is present even if the conductor is not. So what this is also doing is inducing an electric field, and you can imagine with the symmetry of this thing, this is a kind of circularly symmetrical region here where we've got a magnetic field. I'm inducing electric field lines that seem to be rotating, in this case, counterclockwise circles. So even in the absence of the conductor. So this is indeed what we call an induced EMF, an induced EMF, and therefore an induced electric field. So this is different from the electric fields we've seen up to this point, which are produced by static charges. This is now produced explicitly by a changing magnetic field. So a non-electrostatic electric field, okay, is the phrase that our textbook uses. And so in fact, we can imagine our electric field lines, in this case with symmetry, as circular patterns, loops if you will, like this. And again, these are different from the electric field lines that we've seen previously, which originate at the end on static charges. There aren't any charges in this system. And the field lines are now continuous